So over to you.
Yes, thank you, Taive, and thank you very much for asking me to present here. I'm really honored because I'm not a glaciologist, I'm a geologist. As you said, I'm with the Geological Survey of Denmark and Greenland. I have a background working with marine and lake sediments, reconstructing Holocene climate variability in the North Atlantic Ocean. So the presentation today will be quite different from the usual glaciological talks, as I will be talking about changes to the Greenland ice sheet in the past on the basis of marine sediment cores from fjords around Greenland. The reason that I got into working with the Greenland ice sheet was because my good colleague Andreas Alström in 2009, he had a project going on at Helheim Glacier, and he asked me if I could go and take some sediment cores from Semmelik Fjord. And I said, of course, yes, I would love to do that, but there's just one problem. I have never conducted a cruise. I have never been on a boat or anything. So he said to me, yeah, here's the phone number for the dentist in Tasiilaq, and you call him, and then it'll work from there. So I called the dentist in Tasiilaq, and the jungle bells, or jungle drums got ringing in Tasiilaq, and in a minute I had a boat, and from there everything just worked on, and that was then the first of a series of cruises going to other fjords around Greenland in the coming years. So the work that I'm presenting today is based on these sediment cores, and I will focus on forwarding what the sediment cores can tell us about ocean and glacier changes of the big three in the past 2,000 years and into the 20th century. And this work would have been impossible without the help from a lot of wonderful colleagues over the years. And in terms of the data I'm presenting here today, I'd like to highlight my former PhD students, Flores and David Wagner. They have recently graduated. So before I get started on the story of these three glaciers here, what they can tell according to the Marine Archive, I'd like to explain the idea just briefly behind reconstructing glacier changes on the basis of marine sediment cores. So when a glacier slides over land, it incorporates sediment where it is in contact with the bedrock, and sediment. So when following the icebergs they are carved off, they may therefore contain sediment consisting of clay and silt and sand and gravel. And since sand and gravel is they are too heavy particle to travel in suspension in the water column, we can use the finding of such larger grains in the sediment cores as an indicator that an iceberg traveled over the core side. So that the more icebergs that passed over the core side, the more IRD there will be in the core. And of course, real life is not that simple. There are other processes theoretically in a Greenland fjord that could modulate the IRD content. For example, changes to the distance between the core side and the glacier margin, changes to the residence time of the icebergs in the fjord due to winds and melange and so on. So all factors are kept in mind when interpreting the record. Most people think of IRD as a proxy that's linked with glacial reconstructions rather than Holocene reconstructions. And this comes from the studies of the glacial time Heinrich events, where layers of sand and gravel are found in deep sea cores in the Atlantic Ocean, and they are then linked to episodic massive outbursts of icebergs from the glacial ice sheets. We know that Heinrich events, they occur during the final cold phase of millennial scale Dansker-Øske events, just before the rapid warming. But the exact chain of events associated with these sudden armadas of iceberg, that is still debated. But anyway, So conventionally, when we then talk about reconstructing the Greenland ice sheet during the Holocene, the size of the ice sheet at a certain time can be assessed by mapping and dating terminal moraines and investigating glacier-fed lakes. And this will provide us with snapshots of the glacier extension in the past. Records of IRD in fjords, they do not tell us about the size of the glaciers, but what they can do is that they can provide us with high-resolution records of changes to the iceberg production and glacier behavior, and thereby provide us with insight to what drives glacier change on both longer and shorter term timescales, and thereby they can sort of fill the gaps between the snapshots that are provided by the geomorphological studies. So the great thing about these fjords is that they have a quite high sedimentation rate in comparison with, for example, shelf cores and deep sea cores. And this provides us with detailed records that resolves the changes of the 20th century and thereby allows the sediment records to be compared with instrumental and historical observations, so kind of ground truthing the data. In the following, I'm going to show you now 3 examples for the 20th century where a comparison of an IRD record is being done with an instrumental or historical glacier change record. And I think these records comparison, they advocate in favor of using the IRD as a proxy for iceberg production. So we start with the Helheim Glacier. From this fjord, Sermelik Fjord, we analyzed 3 cores, and then we measured the IRD content, and we averaged the calculated signal on the basis of these 3 cores. And when we compare the IRD changes with the changes to the position of the glacier margin, we see that iceberg rafting increases as the glacier margin retreated. And this indicates that changes in the IRD record is modulated by iceberg production. We did the same analysis by Upernavik, in Upernavik Fjord up in West Greenland, because here there is a nice data set of historical observations going back to 1850. So we went there to take some sediment cores, and again we calculated the average signal on the basis of 4 cores. And the same overall pattern of retreating glacier margin resulting in increased IRD again advocates for using IRD as a proxy for iceberg production. One thing that was quite puzzling was that there was a very limited response in IRD to the post-2000s market glacier retreat of this glacier. But what we learned later was that it actually had a tongue during this market retreat. So this might explain that low IRD content because the basal melt of the glacier had sort of carved out the sediment. So our record from Discobugt, it's quite low resolution for the 20th century, but regardless, I think there also seems to be a correspondence between increased IRD and glacier retreat, which again indicate that the retreat phases of the glacier resulted in increased iceberg production. So when we compare the records from Upernavik and Helheim glaciers, some interesting things stood out. In particular, the very marked retreat and iceberg production around 1940. And it is well known that market climate warming on Greenland in the 1930s, likely in response to a positive phase of the the AMO at that time. But we also, in this study, found that the short-lived increases to iceberg carving by Helheim Glacier, they responded or correlated with a negative index of the North Atlantic Oscillation. And this kind of makes sense because, as we know, we have a climate warming during the negative NAO index, and as opposed to the positive NAO index where we have climate cooling on Greenland. So now that we have kind of established the use of IRD as a proxy for outlet glacier behavior, it would of course be interesting to go further back in time beyond the instrumental and satellite era to investigate what these three most productive glaciers had been up to in the past 2,000 years. So before doing so, I think we should just review the climatic variability that has taken place over the past 2,000 years in Southeast and West Greenland. And in this regard, it's particularly interesting to see how the Atlantic waters have varied, since they may affect the Greenland outlets, both by sliding into the deep fjords and coming into touch with the margins, but also because they are linked with the atmospheric climate variability. So the way that these waters here around Greenland, they are conventionally reconstructed, is looking into the sediment cores recorded changes in the species distribution of bottom living foraminifera. And this will help us track changes to the salinity and temperature, and thereby variability in the incoming Atlantic waters. So in our sediment cores in Southeast Greenland, we have looked into using the alkanon paleothermometer. So in very short, this method, it uses the fact that certain single-celled organisms living in the surface water, they produce molecular double bindings in a compound of their cell membrane that's called alkanones. And the number of different double binds in these compounds, it has been known to be water temperature in the water. So when we apply this method to the cores in Southeast Greenland, we are making the assumption that the majority of the alkanones that we detect in the sediment cores, that they are produced in the offshore Atlantic waters by the coccolith ehogs, and then following advected onto the shelf and into the fjords. And this is not a crazy assumption, given that we have excessive blooms of coccoliths in the Irminger Ocean, and also because we know that this water goes onto the shelf and into the fjords. And the data, they also support this assumption. So now let's take a look at what we know about Atlantic water variability by Greenland for the past 2,000 years. Here's a compilation of records from east to southeast and southwest and West Greenland. They basically track the flow of the Irminger current from east to the west. So before we dive into the record, let's be reminded about the broader climatic changes for the past 2,000 years. It has been shown that the specific timing of peak warm and cold intervals, such as the Little Ice Age and the medieval warm period, varies regionally and are not globally synchronous multi-decadal periods. If there was synchronous warming at any time, it was only around 40% of the globe that was affected by it. This is in contrast to the 20th century. The 20th century was the warmest period of the last 2,000 years, and it is characterized by being synchronous across 98% of the globe. So, what we do see, so when these paleoclimate records, they are set together into major compilations. Here we have a compilation of the global ocean sea surface temperature and a compilation of the Arctic temperature. Then what we see is a cooling trend in the last 2,000 years. And this cooling trend is mainly forced by volcanic increasing occurrence of excessive or explosive volcanic eruptions. This trend is interrupted by the 20th century conspicuous warming. That's not shown in these records. So, therefore, when we look at paleoclimate records like these, we will often see multi-decadal warm and cold periods, which departures from an underlying trend, cooling trend, culminating into the Little Ice Age. And this is also the case here when we take a look at the Atlantic water reconstruction from West Greenland. And it's interesting to note that this warming that we see in the early part of the record, and which corresponds in timing to the Roman warm period and also partly the Dark Ages cold period, this warming is actually quite consistent all the way around from west towards South and East Greenland. So keep that in mind. So what is interesting, if we take a look at the Little Ice Age, we see that in Southeast Greenland, there is a strong signal that the Atlantic waters warmed. And this is really a deviation from this general trend of Little Ice Age cooling. So here we are zooming in on a record from Southeast Greenland to try to figure out what happened, what caused this warming. And here we see a reconstruction. This is based on the alkanones of the Irminger sea surface temperature from a sediment core. And what we can see is that there is actually a link between minimum in solar activity and warming sea surface temperature. We see the wolf and the spurrer and the maunder and the Dalton minima. So again, this is not surprising after all, because there has been some climate modeling that has demonstrated that atmospheric circulation, it responds to low solar activity by resembling the negative phase of the winter NAO as well. So yeah, so the response of the ocean to these weaker westerly winds that results from a negative NAO and also from other persistent blocking events across the Atlantic is a wind-driven reduction and shrinking of the subpolar gyre so that it spills onto the Greenland shelf with warm Atlantic waters, and thereby it explains a regional warming of Atlantic waters by Southeast Greenland during the Little Ice Age. I think it's quite interesting to look at the 20th century, because if the subpolar gyre strength in response to solar forcing was the only modulator of the 20th century Atlantic water temperature on the Greenland shelf, then we should have expected a cooling here according to the high solar activity in the 20th century. And this is not the case. And I would think that this points to the influence of anthropogenic warming of Atlantic water reaching Greenland. So with all this warming going on here on the Atlantic shelf back and forth, how did Helheim Glacier then respond to this? So what was interesting was that we found that the sand flux was actually relatively low during the entire period from year 300, from the start of the record, until year 1900. And then it increased fourfold, at the onset of the 20th century. That led us to suggest that Helheim Glacier may have developed a floating ice tongue, or perhaps a very, very dense melange, between year 300 and the early 1900s. And in this scenario, so the debris-rich basal ice from the glacier margin melts out at the spot here and is not transported with the icebergs because they become deprived. And this leads to deposition at the core side further down the fjord. In contrast, then, at the onset of the 20th century, the glacier lost the tongue, and then it became a carbon glacier. And suddenly the icebergs were allowed to keep their sediment and thereby increase the sand flux, RID, as they passed the core side and deposited it there. But this development of a long-lasting floating ice tongue in conjunction with repeated multi-decadal long episodes of warmer water throughout this period, that did not make sense. So what we did was that we looked into sea ice reconstructions from the shelf, and what we found, or what we could see, was that they had consistently high sea ice occurrence, but then there was a unprecedented decrease in sea ice occurrence along the East Greenland current at the onset of the 20th century. So we think that the loss of the tongue and the glacier turning into a carbon glacier at this time could be caused by this decrease in sea ice, because then it kind of it didn't kind of cool the atmosphere to or buffer the glacier from warming. So we concluded that repeated occurrence of warm waters on the shelf during the last 2,000 years as the same magnitude of the 20th century, that was not able to destabilize Helheim Glacier's ice tongue. And that was because it was protected by the cooling effect from the sea ice. And this effect was then lost at the onset of the 20th century, where Helheim became a glacier, in summary. So all this warm water and sea ice in Greenland, in Southeast Greenland, it mixes as it propagates towards West Greenland. So it would be interesting to see the climate conditions in West Greenland, and of course how Jakobshavn Isbræ responded to it. So let's take a look at some sediment cores from Disco Book that was obtained as part of a ACDC summer school in 2014, and that my PhD student David Wagner, later he got to work on them. So in this bay we have the Atlantic water in the form of the West Greenland current, and the West Greenland current is a mixture of the cold surfaced East Greenland current and the warm subsurface Irminger current. So here are some reconstructions of climate. We have the Atlantic water variability from two locations, both here in Discobugt, but also from Veigat up here, another core. And then we have the temperature changes on the Greenland ice sheet on the basis of an ice core. And then we have a sea ice reconstruction on the basis of a sediment core from Edesminnedyb. And what is interesting to note is if the West Greenland current, if it cooled or warmed during the Little Ice Age. We know that the Irminger current warmed in southeast Greenland, but we also know that the sea ice occurrence was quite high in southeast Greenland during the Little Ice Age. And since these two water masses, they mixes into the West Greenland current, and we see that the West Greenland current seemed to cool during the Little Ice Age, then the sea ice influence must have kind of overruled the warming signal. So overall, we see a warm period, transitional conditions during the Dark Ages cold period and the MCA, and then turning into a cooling during the Little Ice Age, and then the early traces of 20th century warming. So the similar IRD pattern in the two cores that are situated 6 kilometers apart, this indicates that the changes, they are spatially homogeneous and they do represent changes to the amount of icebergs that pass over the core side rather than just sporadic localized IRD drop loads. So the long-term trend in IRD, it follows the general long-term cooling trend. So according to land-based studies in the area by Brian and Jakobshavn and others, then Jakobshavn, the terminus of Jakobshavn was located behind its current position in the early Holocene, and then it started advancing during the Little Ice Age, and it reached around year 1400 its Little Ice Age maximum position, and then it remained there more or less until the onset of the 20th century, when it then started to retreat again. So this kind of fits well with the observation of very low RD deposition between 1400 and 1900 that we see in the record. And we interpret it as the result of a reduction in the calving rate of Jakobshavn isbræ because of a more stable and advanced configuration. And a possible explanation for the low RD may also be that the cold atmospheric conditions during the Little Ice Age caused the ice melange in the ice fjord to be more coherent, so that icebergs did not escape the ice fjord. So, a further explanation for the low RD interval could also be that Jakobshavn had a floating ice tongue. So, according to other studies, Jakobshavn, it lost its ice tongue in 2002. And it may be that it have had this tongue for several hundred years. If we assume that the diminished RD is in response to a tongue with submarine melt carving out the sand directly on the spot, and then creating a low sand flux to the seabed further down the fjord. So if we were to be bold and assume that this youngest IRD level, it signifies the response from a calving glacier, then we would have to go all the way back to year 1100 to find equally high level of IRD. So maybe this was the last time that Jakobshavn was in the same configuration as it has been since 2002. But nevertheless, the high IRD and glacier calving in this period, it makes sense because the climate was warm. also variable. And this is in contrast to Helheim Glacier in southeast Greenland, where the Atlantic waters, they were also relatively warm at this time, but the glacier still had its floating tongue. And we think that the different configuration of the two glaciers is because of relatively more sea ice buffering in East Greenland as compared with West Greenland. It's interesting to note these more marked peaks that occur with a centennial spacing. And when we looked into this, we found that we did find solar-like cyclicities of 150 and 210 years, but we only found these cyclicities in the IRD record. Obviously, the climate records are not of high enough resolution to resolve this. But again, this link between solar activity and carving, it does emphasize that how sensitive these glaciers they are to even small climate perturbations. So now we've taken a look at these two very productive glaciers on Greenland. So we will end up with a look at Kangerlussuaq Glacier. And we know that Kangerlussuaq, it retreated fast, as much as 5 kilometers in a short while in 2004 and 5. And then again in 2016 to 18. But we know less of what happened early on because we don't have any observations. Unfortunately, in this study, we cannot go back 2,000 years because we couldn't date the course. But what we can do is that we can look into the 20th century and see how the sediment course kind of could inform us on what happened there. So little is known back in time, but there were some interesting observations during expeditions in the early 1930s. So Wager, I don't know if he's called Wager or Wager, I call him Wager. He came back in 1930 and he noted and took a picture of a floating ice tongue. Then Watkins, he flew by in 1931 and he took this picture where you also see a floating glacier. And then Spender came by in 1932 to make a drawing for some maps, and he was also very thorough, and he also noted this glacier tongue. Then Wager, he came back in 1935, and then he noticed that the tongue had disintegrated and become into bits of icebergs. So this was published then in 1937. And because of this, we went back to find some of Lauke Koch's old pictures, and we found a picture from 1933. And it was quite obvious from this picture that this retreat or this loss of the ice tongue happened within a year. And it was a 9-kilometer retreat. So that's quite a lot. So what also became evident was that the 1932 tongue, it was positioned in its little ice age configuration, because based on multi-beam data from the OMG expedition, Christine Batchelor, she had identified the submarine extension of terrestrial little ice age moraines and the configuration of the 1932 ice tongue, it fitted quite well onto here. So I had been on a cruise in 2012 to this fjord, a really rough cruise where all that could go wrong went wrong, but still I came back with a few cores by miracle. And then Flores Madsen, my other PhD student, he got to work on them. And one of the cores, it had actually covered the 20th century. And it was in this core that, that a prominent layer of IRD was dated to 1932. There's a large error, but there usually is when you do the lead dating. And here we see this prominent IRD peak. So we proposed that this was the signature left by armadas of icebergs on the way out of the fjord. So this is Flores' model he proposed, and he said that during the Little Ice Age, these 300-meter high submarine moraine, and then later on, the glacier it evolved into floating tongue, which was nicely pinned onto the moraine. And then in 1932, the tongue disintegrated, and the glacier may have then sped up to produce a lot of now sediment-rich icebergs that we then detected in a core down the fjord. So then the question is, what caused this collapse in 1932? So a likely explanation is that it responded to this 1930s very marked and well-known warming on Greenland. We know that the Irminger waters, they go into the fjord today, but we don't have a record of subsurface water temperatures inside the fjord as are going back in time. But what we have is an instrumental as well as a proxy record of temperature changes in the upstream Irminger current. And here we see the 1930s prominent warming. So in conclusion, you can say that in similarity with the other two big ones, the 20th century warming was also going after Kangerlussuaq. So this is the conclusions now. What we propose with this work is that that the big three, they experience loss of ice tongues in the 20th century in response to climate warming. And this is not surprising, since the 20th century was preceded by the cold Little Ice Age, which was characterized by atmospheric cooling and extensive sea ice occurrence around Greenland. And what we can use it is to kind of, it provides us with some hints as to what might happen to the ice streams in Northeast Greenland as climate warms further. And the question is then, how unprecedented was this tongue loss? And for Kangerlussuaq, we do not know at all anything. We would have to go back to find out. For Helheim, the 20th century loss of the tongue was unprecedented in at least 100 years, 300, maybe more. For Jakobshavn, the loss of the final minor tongue in 2002, it was likely unprecedented in 900 years, around since year 1100. So why were these two glaciers so differently configured before the Little Ice Age? So we had also found this warming of the Atlantic waters by Southeast and West Greenland between year 300 and 900. So this was a time that was characterized by quite frequent warming periods lasting several decades. And these episodes, they occurred across the globe, but they were not globally synchronous. So by Helheim Glacier, concurrent high sea ice occurrence buffered the glacier, so it had a floating tongue. Whereas by Jakobshavn, this warming, it resulted in a highly iceberg producing calving glacier. So, yes, to finish up, I'd like to reach out to the IGS community and say thank you for listening to this, a lot of curves you were presented with. And if you have interesting ideas for this work and would like to collaborate or anything, so I would be happy to hear from you. And as a little commercial for next week, Hester Jescott will be giving a presentation called The Journal, the Annals, the Glaciologist, and the editorial process. Yeah, thank you.
Hi, Camilla, thank you very much for that. Has anyone got any questions? The way that we've done this usually is that if you just type yes in the chat, then we unmute you and we do it all verbally. It's kind of more friendly than typing messages, or alternatively you can type questions into the chat if that's easier. So any questions for Camilla? Yes, Fiamma, yes, go for it.
Hey Camilla,
Hey,
great talk.
Thank you.
Thank you for giving it. I know it's late over at your side of the world. So I was curious about the possibility of using alkenones. You talked about them in Sermelik, and I know that work, but what about some of the other fjords?
Yeah, I think that the reason that it seemingly works, what could be, is that there are other organisms that can produce these alkanones, and they might not have the same calibration. So they would, if you have them and you treat them like they were EHOCs, then you would get a wrong signal. But it would require that you had a lot of the other alkanones. And I think for other fjords, I'm not so sure that the Atlantic water would be so prominent to overrule that potential signal from other haptophytes disturbing the signal. But I think it's something that has to be investigated by going back and taking some more cores and doing DNA and stuff like that. But yeah, I don't know. It has been applied in, for instance, in Discobugt, the method alkanone. I can't remember the results right now, and yeah.
Great, thank you.
Any other questions for Camilla? I guess I'll ask you one, which is which areas would you go to? What are the key areas that you feel like we don't know enough about in terms of the historical record at the moment?
That's a good question. I do think that more of these deep troughs in Southeast Greenland would be interesting to look at, but of course also 79 Fjord, but people are already looking into that. I think that there are a lot of studies going on also with Petermann Glacier. Yeah, maybe by northwest Greenland, further north of Upernavik. I guess we would have to do everywhere. I think all areas are equally important, because every time we investigate an area, we learn something new, and the glaciers, they have their own life and their own setting and their own behavior. There are some trends, but I guess if we are really to get an overall impression, we have to have a lot of records, and we have to be able to put them together and take out the noise and look at the common signals. So yeah, it's difficult to answer that.
Thank you. Any last questions for Camilla? Okay, it looks like not. So it just remains for me to say thank you very much for a great talk. And I'm looking forward to next week's talk, which I think is going to be a little bit different from some of the science talks we've had so far. And we'll have to see what Hester has to tell us. I'm going to get all the grad students in Swansea to make sure that they come and learn how to write their papers in a way that will get them accepted. So thank you very much indeed, Camilla.
Thank you.